Welcome to Mrs. Lee's Chemistry Academy, where no students are left behind. Today we're going to cover the last section on reactions unit on combustion, synthesis, and decomposition reactions. This is tied to the learning objectives from the College Board, that the student can translate an observed chemical change into a balanced chemical equation and justify the choice of equation type. That the student is able to design the plan in order to collect data on the synthesis or decomposition reaction of a compound to confirm the conservation of matter and the law of definite proportions. The student is able to use data from synthesis or decomposition of a compound to confirm the conservation of matter and the law of definite proportions. Combustion reaction is in which a substance combines with oxygen in the air to form one or more oxygen-containing compound with heat released. The first one we're going to try will be writing the combustion reaction of propane, C3H8, burned completely in excess oxygen. So I write C3H8 gas, propane gas, plus oxygen, gas from the air, to yield carbon dioxide gas and water vapor. Sometimes it can be water liquid. And in the combustion of hydrocarbon, the compounds formed are always carbon dioxide and water. So now we balance the carbon, put 3 in front of CO2, balance the hydrogen, put 4 in front of water, and now I count the oxygen atoms on the right. I have a total of 10 oxygen atoms, so I balance with 5 diatomic oxygen molecule to completely balance the oxygen atoms. The next one is ethylene gas, which is the welding gas, C2H2, burned in air. So again, this is going to combine with oxygen, diatomic molecule in the air, to form CO2 gas and water. The carbon, I need 2 carbon atoms on the right, so I insert a coefficient of 2. The hydrogen is already balanced, so now I have a total of 5 oxygen atoms. So I go ahead and multiply the oxygen O2 by 5, but because it's diatomic, that means I need to double everything, so I go back and insert a 2 in front of the ethylene and change the CO2 to 4 moles and insert a 2 in front of water. The next one is the combustion of sulfur in standard state, and we have sulfur, solid, and oxygen diatomic molecule to form sulfur dioxide gas. The next one, dimethyl ether burned in air, so we have C2H6O plus O2 forming CO2 and H2O. And I would balance the carbon by inserting a 2 coefficient in front of CO2. I insert a 3 for the water to have a total of 6 moles of hydrogen atoms. Now I count my oxygen. I have 7 on the right, and I already have 1 with the dimethyl ether, so I multiply the O2 by 3, and this is balanced. Pure solid phosphorus, white form, burned in air. This is actually P4, solid, plus oxygen, gas, to form P4O10. This is a solid here, tetraphosphorus dicoxide, and I multiply the O2 by 5. The next one. Solid copper 2 sulfide strongly heated in air. I have copper sulfide, CuS solid, plus oxygen. And you can basically predict the product by actually splitting the copper sulfide. So copper will combine with oxygen to form copper oxide, solid. And the sulfur will also combine with oxygen to form SO2, sulfur dioxide gas. I balance by putting a 2 here. So I put 2 in the copper sulfide, 2 in the SO2, and now I have 6 oxygen. I put a 3 here, and everything is balanced. So this is a recap of my earlier work in combustion reactions. You may want to pause the screen to follow the work and practice writing it yourself. The next kind of reaction is synthesis, where a compound is made from the elements A plus B to make AB. So let's practice with writing it. Aluminum foil, 8L solid, placed into bromine liquid to form aluminum bromide. And solid in the liquid, I may call that AQ. Okay, so I balance the bromine by putting 3 here, and 2 here, and 2 for the aluminum, and that's balanced. With iron metal, heated with sulfur, Fe solid, and sulfur solid, to form the iron 2 sulfide solid with brand new properties. The next one, lithium metal strongly heated in nitrogen gas. I have Li metal with N2 gas to form lithium nitride, written as Li3N, which is a solid. So now I balance the N with the 2 here, coefficient, and balance the lithium with 6 over here. The next one, excess chlorine gas passed over hot iron filings. So I have chlorine gas here and iron. Now, because of excess, so it is going to form FeCl3. And I balance the chlorine by putting 2 here, 3 here, and a 2 here. So the mole ratio is 3 moles of chlorine to 2 moles of iron. So that's what it meant by excess. So a recap of my earlier work. You may want to pause the screen to follow this and practice writing it. Now the next kind of reaction is decomposition, in which a compound is broken down into its elements or simpler compound by heating or by electrolysis. Solid mercury 2 oxide decomposes as heated in an open test tube in a film hood. So we have HGO solid heated to form mercury liquid and oxygen gas, and I balance by putting 2 for the HGO and 2 for the mercury. The next one, solid ammonium carbonate decomposes as is heated, so I write NH4 2 CO3 solid. When it's heated, I get ammonia gas. And I get the water and the CO2 gas. And I balance by putting 2 in front of the ammonia. And I believe everything is balanced. The next one, hydrogen peroxide, the one that you buy from the drugstore. And when you open the cap or expose it to the air or sunlight for some time, you actually get water, liquid, and oxygen gas. Now, I balance with a 2 here and a 2 here. This is actually called a disproportionation reaction, in which the oxygen atom is both oxidized and reduced. The next one, solid sodium hydrogen carbonate. By the way, you should know this is baking soda in your kitchen. NaHCO3 solid heated to form sodium carbonate and water and CO2 gas. And we balance with putting 2 coefficient in front of the NaHCO3. So iron 2 sulfide heated strongly. I have FeSO3 solid heated. I get the FeO iron 2 oxide and SO2 gas. Sulfur dioxide evolved. Solid copper 2 sulfate pentahydroheated gently. So this is a hydrate of copper 2 sulfate attached with 5 moles of water. When I heat it gently, I actually separate the anhydrous copper 2 sulfate from the water. So here is a recap of my earlier work for you to follow. Okay, here we have a problem involving designing of an experiment. Design a lab to collect data on the decomposition of a compound and to confirm the conservation of matter. So this involves the decomposition of potassium chlorate into potassium chloride and generating oxygen gas. So the procedure, first we mask an empty test tube. Then we put 1 gram of manganese dioxide into the test tube and mask it again. Now this is a catalyst. And then we add, say, 3 grams of potassium chlorate to the same test tube and mask it again. Now we mix them well, and we stopper the test tube and heat it strongly over a burner, and we collect the oxygen gas by water displacement. And then we mask the test tube after all the potassium chlorate has been decomposed, forming potassium chloride, leaving it behind in the test tube, and after it is cooled. So here's a diagram of what it would look like. You have a test tube putting the potassium chlorate and the manganese dioxide catalyst in it, and we're heating it so that the oxygen gas evolved will be collected by water displacement into that container, fully filled with water and inverted into a water bath. Data collection. Let's say we mask the test tube to be 20.785 grams. Then we put in the catalyst, manganese dioxide, we mask it again. And then we put in the potassium chlorate and we mask it again. Now after heating for some time, we let it cool, we mask it. Now we have the residue, potassium chloride, and the MnO2 in there, 23.740 grams. Now let's say we measure the volume of gas oxygen collected to be 967 milliliter and at temperature of 24.0 degrees C, and we measure the air pressure to be 1 atmospheric pressure, and we look up from the table to find the vapor pressure of water at 24 degrees C, which is 22.38 millimeter mercury. Now the calculation. First, we need to find the mass of the potassium chlorate that we place into the test tube. So we take line 3 of the data chart minus line 2 from the data chart. Then we convert it into moles of potassium chlorate. Now we find the mass of the potassium chloride residue left behind in the test tube. So we took line 4 and subtract line 2 from it, from the data chart. And we convert it into moles of potassium chloride. Now, because we collect the oxygen gas over water displacement, so we must equalize the air pressure externally to the internal pressure, and then we must account for the vapor pressure of water. So the pressure of the dry hydrogen, oxygen, is equal to the pressure of air minus the vapor pressure of water. So that turns out to be 738 millimeter mercury. Now we can use the ideal gas law to find the moles of oxygen by pressure times volume over R, ideal gas constant, and temperature. We come up with 0.0385 moles of oxygen. Now then we look at the mole ratio between potassium chlorate and potassium chloride and oxygen from our calculated numbers, and then we can divide them into by the smallest number into whole number ratios and multiply that by an integer of 2. Now we have a mole ratio of 2 to 2 to 3. And because the calculated mole ratios are consistent with the stoichiometric mole ratio in a balanced equation, then we have verified the law of mass conservation. Practice problem 2. Design an experiment for synthesis reaction to collect data to confirm the law of definite proportions. First, we take a clean, empty crucible with a lid and we mask it. Now we're going to take about 20 centimeters in length of loosely coiled magnesium ribbon and put it into the crucible and mask it again with the lid. Now we set the crucible with the lid on a clay triangle supported on the ring stand and heat it strongly with a burner for 10 minutes. During the heating, a bright light will be produced and we keep the lid on to avoid loss of product. When all the magnesium has fully reacted with oxygen in the air from the combustion, a white powder magnesium oxide will be formed. And we should cool the crucible and mask it again with the content and the lid. Now we should repeat heating a couple more times until we get constant masking, because we wanted to be sure that all that magnesium has been converted into magnesium oxide. And if we want to get more data, we would do it a couple more trials to get other results. The data collection. First, we should find the mass of the crucible with the lid, 25.37 grams. Now we put the magnesium in it and we mass it again, 25.64 grams. And then at the end of the combustion, we mass it, we heated it 3 times and massed it 3 times after it's cooled, and we got 25.80 grams, which is quite consistent with the previous weighing of 25.79 grams. Now how do we calculate? First we calculate the mass of magnesium by taking the container with the magnesium minus the empty crucible with the lid. And then how do we find the mass of magnesium oxide? That is after the final heating, that line, we subtract the mass of the empty crucible from it. And now subtracting magnesium mass from the mass of magnesium oxide, we know then we get the mass of oxygen reacted. Now we convert the moles of the mass of magnesium into moles of magnesium, 0.011 mole. And we also convert the mass of oxygen into the moles of oxygen. And notice how close they are, about the mole ratio of 1 to 1. There the formula of the magnesium oxide is MgO, 1 mole of magnesium combining with 1 mole of oxygen. So to sum up what we have learned in this lesson, first, we learned how to write combustion, decomposition, and synthesis reactions and predict their products. 2, we learned how to design an experiment for the decomposition and the synthesis reactions. And lastly, we learned how to analyze the data from the experiments to confirm the law of mass conservation and the law of definite proportions. I hope that you have found the above lesson to be helpful to you. I welcome any comments from you, and I hope to see you again next time.